Alright, so today what we're looking at is optimization. This is the last of our applications that we're looking at, optimization. And before we get into doing any problems, I want to make sure that we understand what optimization is. What are we talking about when we're talking about optimization? What?
Make something like better or the best it can be.
Yeah, make something the best it can be. We want to, if we want to optimize it, we want to make it the best it can be. Now, the definition of what the best is will vary from problem to problem. Okay? In one case, if we're dealing with money, in one case it might be the best for that money to be the highest it can be. In another case, it might be the best for the money to be as low as it can be. So, optimization, you know, what we're defining as the best will vary from problem to problem. Okay? Now, your book actually gave a really, what I thought was a really good problem-solving method for these. So I want to outline that briefly, and then we're going to actually use this outline to solve two of our problems. So we're going to see where, you know, this is a very general outline. There are times when parts of this won't apply, but I thought it was a really good tool that we could use to kind of guide us through some of these problems. First of all, when it's appropriate, draw a large, clear diagram of the situation. Now, obviously, if we're talking about a company's profits, that's not something that you can really draw a good picture of, okay? But if we're talking about area or volume, or if we're talking about some kind of a periodic function and we're modeling it or something like that, then drawing a picture can be really, really helpful, okay? Secondly, construct a formula with the variable to be optimized as the subject. Now, what does that mean? Basically, when it says we want to maximize the profit needs to be the subject of your equation. Now that just means that's going to be the dependent variable. Okay? That's our dependent variable. And then notice it says it should be written in terms of one convenient variable or independent variable. Okay? Okay? It says you should write down what domain restrictions there are on X as well. Now, this is going to give you your interval of possible answers, okay? And while the mathematical domain certainly applies here, we can't have denominators equal to 0, we can't take square roots of negative numbers in a word problem. What also applies, though, is what I call the logical domain, okay? A logical domain. And what I mean by that is, in terms of the situation, what are values that may be mathematically correct, but logically don't make any sense? Okay? For example, if we're talking about profits and we're trying to maximize profits, then obviously I don't care about the negatives. Okay? So we could limit our domain based on what the zeros of the function would be, because we don't need to look at anything outside of those. Or, you know, you might be dealing with area, and there are certain values that will make your area 0. Or it might make the area beyond the biggest area you want. Okay? Let's say we're trying to minimize how much, you know, fence we're using to get around this certain thing. Okay, but we also don't want the area to be bigger than a certain amount. Okay, so we're minimizing the fence to get it within a range or something like that, but we don't want it to go higher than a certain value. So we could have a logical domain in that sense. Okay? Then we're going to consider the first derivative. Okay? Find the first derivative and the values of x that make that first derivative equal to 0. What are we finding here?
Critical value.
Critical values, okay? Or stationary points if you like the book's words. Okay? We're finding critical values. Stationary points, critical values. Here comes where we're actually finding the answer itself. Okay? And there's three things that we need to consider. First of all, says for restricted domains such as x between two values, and notice it has to be able to equal those values, the maximum or minimum may occur either when the derivative is 0, so at that critical value you just got, at an end point, that's an easy one to forget, or probably the least common one is going to be a point where the derivative is not defined. Okay, that one doesn't show up too often, but it's possible there as well. So here we have where we will find our optimal solutions, where the derivative is 0, where we have an endpoint of the interval, or possibly if our derivative is not defined, it could be there as well. Now, one thing you do need to make sure you do, excuse me, and you could even do this as part of step 3, but showing that that critical value that you gave is actually a value that gives a maximum or a minimum point. And you can do that a number of different ways. We've seen that using a sign diagram. If you see a change in direction, we were decreasing, now we're increasing, so we know that that's a min point. Or we were increasing, now we're decreasing, that's a max point. Or you can use the second derivative test. Okay? If you have a critical value, and it's in an interval that is concave down, then you know that that critical value gives us a max point. Okay? If your critical value is in an interval where we are concave up, we know it's going to be a min point. Okay? Or the graphical test. That's just basically saying you know what the graph looks like, you know that's going to be a max point, or you know it's going to be a min point. Like if you have a quadratic or a cubic, you're familiar with what it looks like, you know it's going to be a max or min point. And then finally, and this is where some of you, it's not really a weakness, it's just we need to make sure we follow through with the problem. Make sure you write your final answer. You don't necessarily have to do it in a complete sentence, but make sure you clearly give the answer to the problem with units of measure. Okay? With units. Alright, so if it's money, label it as money. If it's an area or if it's lengths of sides, make sure you label it with whatever the measurement's going to be. Okay? So, that's our overall structure. Let's actually use it, okay? Let's take a look at a problem here. We have a 4-liter container, and it must have a square base, vertical sides, and an open top. Alright, so it doesn't have a lid. Find the most economical shape which minimizes the surface area of material needed. Okay? Now, first of all, what shape are we talking about? Okay, it could be a cube, it's rectangular,
Has a square base.
has a square base, but the sides are not necessarily the same length too. Do you remember what that's called?
Rectangular.
A rectangular prism, okay? A cube is a type of prism, but... Alright, so we have this rectangular prism here, okay? I'll see how well I can draw this in perspective. There we go. That's halfway decent at least. Alright. Those of you artists, don't get caught up in trying to make your picture perfect. Just get a decent looking picture. Okay? Now, it says that we have a square base. So I'm actually going to label the sides of my base X. And then it says it has vertical sides, but I don't know how long those are either. So I'll have to use a Y for now. Okay?
Plus 6.
But guys, this is important because we need to make sure that we actually understand what we're dealing with. Okay? And we're careful not to make assumptions like, oh, all three of these are the same. Or, you know, we have it the right shape at least. Now, here comes, that was all just step one. Step two, we need to find an equation or a formula for the variable to be optimized. What variable are we trying to optimize here? Our surface area. Okay? Our surface area. Now, question, how do I find the surface area of the box? Remember, the top is open, so we don't need to include it.
X squared plus 4xy.
Okay? X squared is going to be the bottom, and then each side is x times y, right? That's x times y. So there's 4 of those, so plus a 4xy. We have a problem here, though. What's our problem? Yeah, we have 3 variables. We have one dependent variable, s, and then we have these 2 variables over here. We only want one independent variable. And that's where this fact right here comes in, 4 liters. And this takes a little bit of extended knowledge here. All right? How do liters relate to the lengths of sides?
Is it 1 cubic? So, a cubic centimeter is a milliliter.
Yes.
So then you just multiply that by 1,000.
Yes.
So 1,000 cubic centimeters is 1 liter.
Yes. Good. So, our volume here, since it's 4 liters, our volume is 4,000 cubic centimeters. If you've ever been at the doctor and they're talking about cc's, that's what they're talking about. They're just talking about milliliters. Okay? So, you know, and actually if you get medicine sometime, even over-the-counter medicine, sometimes they'll give you a thing that says cc's. 1 cc is just a 1 milliliter. Okay? So, that's helpful because how do you find the volume of a box like this? Yeah, length times width times height. So x times y. So I know x squared y equals 4,000. So that means I can now write y in terms of x squared. 4,000 over x squared. Okay? So now I can actually write this function s as a function of just x. Okay?
Would be x squared plus 16,000
Yeah, x squared plus, when we plug it in, we'll need to, one of the x's will cancel with this x. So we have 4 times 4,000 is 16,000. And that'll just be over x because one of the x's canceled. Alright? This is really probably the most challenging part of these problems, is getting your equation right. Once you get that, then we're back to doing the same stuff we've been doing for like 3 chapters now. Okay, get your derivative, find a critical value, test it, and give an answer. Alright. So here, before we do go any further, we should give a domain. What is the domain of x?
Greater than 0.
X has to be greater than 0. Now, x cannot equal 0 because of this. How come it has to be greater than 0? Can't have a negative surface area, okay? There's that logic part of it coming in to play here as well. Okay? So at this point, we want to find a minimal surface area. We want to minimize this function. So you guys take the next 3 parts, the last ones at the bottom, just writing out the full answer. We want the dimensions that are going to give us that minimal surface area. Okay? So go ahead and take a couple minutes here and try to find that, now that we have our function.
You have to use the coordinates. So it's u prime is 0. You have to use the quotient rule. So it should be u prime minus r squared. Over x squared. It's 2x plus 16,000 over x squared.
Remember, rewriting the original function would be helpful.
u v prime is
Actually, you.
I started to wrong.
V squared, but it's we just double the
What?
x over the body.
Why is the original?
what's the y? Is it
It
u
looks so
v
much
prime?
like it's like polymer.
Explain.
Because like u prime v plus v prime. The first part is like open top. The first part is 0, and the second part is everything else comes down. How first is essentially one base.
I remember.
Here's your x by x, and then you have x y.
Oh yeah.
Pizza.
Mosquito.
Boy.
I'm nearly as good as
I don't know. I mean,
X equals
Oh, yeah, the one's involved in the other one's circle.
oh, you make the same yeah. Oh, you just swap the sides. Yeah, but at the same time, you cannot just simplify this.
And I got zero.
Because
Wait, what is that? Okay.
Oh, wait,
because see, you have this and
You
you
really
really
think it's gonna work?
and this
Yeah.
cannot just go in the
That's the question. That's fine.
The 2x cannot just go in the yeah. So I don't think there's a point, like, to do this, which you're thinking of to simplify, you will have eventually x to the third power of 1.
It's better than 3D. Yeah, but it's not.
This thing can hold only 2 hours. No, it's okay. I'll just charge it.
Oh, okay. I thought you said that's where.
Maybe there's another one.
Oh, you should
There will be.
It's your last birthday to people that actually matter. You have to make one.
You'll never find anyone else.
Wait,
Whatever you say.
Alright, what'd you get for your critical value?
wait.
What do we get? X equals 20. Listen up. We set it equal to 0. I multiplied both sides of the equation by x squared to get the x squared out of the denominator. We end up with the cube root of 8,000. Cube root of 8 is 2. Cube root of 1,000 is 10, so that's 20. Okay? And what are our units of measure here? Centimeters, right? Because we were in liters, so we converted that to cubic centimeters. So this is centimeters. Okay? Now, we can confirm that that is actually a min point by doing a quick sign diagram here. Alright, if I put 20 down, and I test something to the left of it, like 1, I can't test 0 because it's undefined at 0. Alright, but if I test 1, 2 times 1 is 2, minus 16,000 is a big negative number. Okay? So I know that we're decreasing on the left side because it's negative. And if I were to plug in something bigger than that, like say, I don't know, 100? No, let's not do 100. Let's say 30, okay? I'd have 60 minus 30 squared is 900, so 160 divided by 9, okay? 160 over 9 is smaller than 60. That's really all you have to notice, okay? So I know it's going to end up being positive. So I'm increasing now. When you see that sign change, you know that you have an actual min point. Okay, they're at 20. So we found the derivative, we found the critical value. You know what, I should probably put this down here because that's really what we were doing. We were testing to see if we had a min value, and we found it. The min at x equals 20 centimeters. I don't have any endpoints to test, okay, because we have to be greater than 0. Even if I tried 1, I mean, plug that into the original function and you have 1 plus 16,000. Okay? That's going to give me something really, really big, as opposed to if I tried 20, S of 20 is going to equal 20 squared plus 16,000 divided by 20. Okay? Well, that's 400 plus 16,000 divided by 20 is 800. So I only have 1,200 square centimeters. And it's squared because we're talking about area. Okay?
So that's the final answer.
Well, our final answer, not quite. It says give the shape that would optimize, that would minimize your surface area. I only have X so far. I need to go back and figure out what Y would be. Remember, Y is 4,000 divided by X squared. Alright, so our final answer is going to be the base is 20 by 20 centimeters. Okay. The height is, remember, Y is 4,000 divided by X squared. So 20 squared, that's 400. So what's our height? 10. And that gives a clear answer. Okay? Our base is 20 by 20, our height is 10. That'll give us the minimal amount of material to hold 4 liters. Yes?
So what was the point of finding 1,200 centimeters squared?
Just if I wanted to compare it to, say, S of 1. S of 1, we ended up, you would get 1 plus 16,000. It was 16,001. Now, that's not an endpoint because technically it's greater than 0, so we could test 0.01 or 001. But just to show you, in this case, the critical value is going to be guaranteed to be the min as long as we know that there's a sign change there.
So when you get your critical values, you do the sign test, and if the direction changes around it, then you know that that's the minimum or maximum.
Yes.
And what happens if it doesn't?
If it doesn't, then that means that was like a plateau point.
So
There may not be a solution to optimize, so, yes. And by the way, if you're asked to show that something is a minimum point or a maximum point, you're expected to do something like this. You can do it a couple of different ways. You can either do a sign diagram for your first derivative, or you can test your second derivative at that point. Okay? If I had gotten the second derivative and plugged in 20, I would expect it to be what, since we have a minimum? I would expect our second derivative to be what at a minimum?
Concave down. Up.
Concave up, so our second derivative would be?
No.
Positive. Remember, when the second derivative is positive, we're concave up. Alright? So that's when they're talking about the second derivative test. We could have taken S double prime of X, and that would have been 2. Let me see here. Yeah, that would have been 2 plus 32,000 X to the negative third. Well, that's positive, this is positive, we're plugging in a positive, it's going to be positive. Okay? S double prime of 20 is 2 plus 32,000 over 20 cubed. And you could just show, and this would be enough to show your work, you could just say that's greater than 0. Okay? And then you could say for certain that is a minimum point. Okay? So if you have a critical value and your second derivative is positive, you know you have a min. If you have a critical value and your second derivative is a negative, then you know you have a max because you're concave down. If it equals 0, that means it was a plateau point. You should have already kind of noticed that. But you don't need to do both of these, but you should do one or the other to show that it is indeed an extreme. Alright, let's start looking at our next one here. We've got enough time to at least get most of this one done. Okay? This is actually from the homework section in the book, but I thought it would be a good one to use as an example. So let's read through it here. When a manufacturer makes X items per day, the cost function is C of X, and you see it there, dollars. And the price function, that means how much they're selling all of them for. So that's like their income. The price function is lowercase p of x, dollars per item. Okay? Find the production level that will maximize profits. So which one of these are we going to differentiate? Both, kinda, because are either one of these what we're trying to optimize?
We
No.
want to see what the minimum cost is and the maximum cost.
Maybe, but actually if you think about it, the price function, the highest price would be 15 when x is 0. Okay? But we don't want to produce nothing, right? How do you calculate, what are we trying to optimize here?
The marginal cost.
Not marginal cost, just what are we trying to,
Efficiency of production, like efficiency of production, and so you're trying to get profits, so you want to optimize.
okay, profits.
Price
We
maximize.
want to optimize the profits. So we're going to have, I'm going to call it capital P of X. And that's going to equal, how do we calculate our profits in terms of our costs and how much we're selling stuff for?
Price minus cost.
Yeah, the price that we're going to sell it at minus the cost at what it cost us to produce it. Okay, and notice this is per item. So each item, when we produce 100 of these, each item would cost C of 100 to produce, and we would be able to sell it for P of 100. Okay? So the nice thing about this is we can actually just subtract the two functions from each other. Okay? So P of X is going to equal, we have 15 minus 720, that's a negative 705. We have a negative 0.002 minus 4, so that's a minus 4.002 x, and then minus a 0.02 x squared. Let me move this over.
Wouldn't that be minus 715?
720 minus 15.
Oh, 720. Oh.
Yeah. So there's the function that we're actually wanting to work with. Now, are there ways where we could figure out like where cost is at its lowest and price is at its highest and try to work something out. Yeah, we could try to do that, but this is a more efficient way. We have a function that is actually focusing on its dependent variable is what we're trying to optimize. Okay? Now, we want to maximize profits. So, obviously, we want it to be at least 0, right? Okay? We want it to be at least 0. Now, this one, while we don't need to consider anything that would make it a negative, what do you know about this function right here in its shape? What's it going to look like? Okay. It is concave down. It's a parabola, right?
And it's not very well.
And it's going to have a max. What feature there tells us we're going to have a max?
X squared.
A negative where?
X squared.
The negative x in the x before the x squared. That's right. Okay? So we don't need to overthink. Here's where, guys, here's where we don't necessarily have to use the sign diagram or the second derivative test to show that it is going to be a max point once we get our critical value, because it's a parabola. So you could just sketch your p of x and show that you're finding the max point, and you're confirming then that you know it's a max. All right. So let's go ahead and find our first derivative. All right. What is p prime of x?
2 times negative, times negative 0.02 x
Okay.
minus 4.002.
Good. All right. Just to keep it in the order it was in, it doesn't matter, but we have the minus 4.002 minus 0.04x. All right. I want the critical value where that equals 0. All right. So yeah, if I have negative 4.002 minus 0.04x equals 0, what do we end up getting? Okay. You know what? Can we get this backwards? Cost and price. If so, I don't think they make. Well, no, because that would give us a minimum.
Can we just multiply by -1? So when we're trying to find x in that first derivative.
Well, but that would still make a -1, a negative 100.05.
That's true.
It depends if it's like their cost or the customer's cost. Or like their
Yeah.
customer's price of business.
The only thing is, if we did turn it around, then we wouldn't have a max, we'd have a minimum. So that would kind of mess that part up. So this is outside the range. This is outside the range of possibilities. because we don't want x to be negative, because that is something we can look at in the domain. X has got to be greater than or equal to 0, because you can't produce negative, well, you can't produce negative number of items per day. Okay? So this one's got a little bit of an issue. Let me see if maybe there's a typo in there somewhere.
Maybe that's
Why not?
Hang on. Okay, we made, this one is not defined real well. Okay, let's take a look at this. It says the cost function is this many dollars, period. The price function is this per item. Okay, so actually when we did this, we should have taken the price per item times the number of items. So they intentionally made it annoying. So let's take a step back and figure out our function again. Do you guys get that? This is dollars per item. This is overall cost for producing everything.
But how are you supposed to, like, I would assume that they were both the same. You know, like if it was per item, I
I
would
would have
assume
too.
that
I
the
think it's a
cost would-
poorly worded
Yeah.
question. But now that we know x times p of x is 15x minus 0.02 x squared. So, okay, now when we subtract, here we go. Now when we subtract, p of x is going to equal 720, or a negative 720, okay? 15x minus 4x is a plus 11x, okay? And negative 0.02 minus another 0.02 is minus 0.04 x squared.
Yes, the 1.002.
What is it? Oh yeah, I lost a, there we go. So that'd be 0.022. 0.022 x squared. Okay. Now we still want x greater than 0. Alright? So let's go back here and rework this a little bit. Okay? When we get our derivative, it's going to be 11 minus 0.044x. And that's good because that'll now give us a positive answer for x. Okay? So when we set this equal to 0, we will then get x equal to what? 11 divided by 0.044? 25? Alright, so 25 units. Oh, wait, yeah. 250? 250, okay. So 250 units. Okay. So, there we go.
How you do